Hello, welcome to the course PH6B13E Computational Physics. The contents of today's lecture is taken from Numerical Methods for Scientists and Engineers by K. Shankar Rao. We will continue to discuss topics from Module 2, Numerical Methods in Physics. In the last class, we discussed about Taylor series expansion of some of the common trigonometric functions like sin x and cos x. In today's class, we will talk about another numerical method known as curve fitting. In fact, this is one technique, numerical technique, which you will be going to use extensively if you get into scientific research. Because many a time, you will need to apply a mathematical formula to approximate the behavior of a physical system. In such cases, curve fitting is one technique which you are going to use. So for simplicity, let's start with an experimental observation involving two variables. And the question is, can we find a relation, a function connecting these two variables? And if you are able to find such a function, that is known as the theoretical curve or theoretical function which fits the experimental data. So if you take the example of a resistor, an ohmic resistor, suppose you do not know anything about the Ohm's law. Okay. So how do you perform an experiment? You apply a certain voltage and monitor the current. Okay. Suppose I apply 2 voltage, then I see 1 ampere current is passing, then I increase voltage to 4 volt, then current increases to 2 ampere, 6 volt, 3 ampere, etc. Okay. So I have 3 data points, and these data points I obtained by performing an experiment. Okay. So these are known as experimental data. Now, using this experimental data, I will try to see what's the relation between voltage and current, or what is the function which connects these two variables. Okay. So when I take the ratio of voltage to current at each of the points, 2 volt by 1 ampere, this is a constant which is 2. At the second point also, voltage by current is a constant which is true for the case of the third point as well. So now I know that voltage by current is a constant throughout this data range, and that's how I come to the Ohm's law, which says that voltage by current is a material constant known as resistance. Okay. So here when I write V equal to IR, this is a function which connects the variable voltage and the variable current. So this is known as the theoretical function which fits the experimental data. So we are talking about two kinds of data here. One is the experimental data which you obtain by performing an experiment, and you have a theoretical function or theoretical data using which you fit the experimental data. Now, when you plot V equal to IR, that's what I have shown here in the form of a straight line. You can see that the theoretical line matches with the experimental data. In other words, the theoretical curve passes through most of the data points. If you take another example here I perform the same experiment at 2 different temperatures, one at room temperature and one at high temperature, and I have the experimental data points here shown in the form of the pink and blue dots. Then I fit them with a straight line, which is nothing but my Ohm's law here. So this kind of a fit which passes through most of the experimental data points is known as the best fit function. So the problem of finding the equation of an approximate curve which passes through as many data points as possible is called curve fitting. In other words, curve fitting is the way we model or represent a data spread by assigning a best fit function or best fit curve along the entire range. Now, what are the advantages of fitting an experimental data with a theoretical curve? First thing, it will help you to understand the trend in the data. So when you fit these three data points with a straight line, now you can immediately make out that there is a linear relation between voltage and current. So the trend in the data is revealed by the theoretical fit. Second, it also allows us to make predictions of how the data series will behave in the future. For example, here I have information only up to 6 volt. What happens at 8 volt? I do not have the experimental data for it. But when you fit the data with a straight line like this, now I can extrapolate, and from these data points I have already found out that the ratio of voltage to current V by I is a constant. In this case R is 2 ohms. So using this equation, now I can find out what will be the current corresponding to 8 volt. Remember, I do not have the experimental data corresponding to 8 volt, but I can theoretically calculate what will be the current at 8 volt. So from this equation I can write V by R equal to I. So at 8 volt, current is going to be 8 volt divided by R, which is 2 ohm. So 8 by 2 is 4. So at 8 volt I have 4 ampere current. So I can extrapolate, I can make predictions, or I can find what will be the current at an in-between point. For example, at 5 volt, what will be the current? Once again, I do not have the experimental data for it, but theoretically I can calculate, because now I know the function. Now I know the relation between V and I. So when V equal to 5 volt, V by R, 5 by 2, which is going to be 2.5 ampere. So I can make all sorts of predictions using the best fit function. Now the question is, how do you find the best fit? There are different methods, like method of group averages, method of moments, and least square method. In this class, we will talk exclusively about least square method. So once again, you are going to perform an experiment and get some experimental data. Then you fit the experimental data using a theoretical function. Okay, so imagine that x1, y1, x2, y2 all the way to xn, yn are the set of xn experimental data. For example, if you go back to the previous example, x1, y1 is nothing but 2 volt 1 ampere, x2, y2 is 2 ampere 4 volt, x3, y3 is going to be 3 ampere 6 volt. So these are the experimental data. Now you want to find the relation between x and y, or in other words, you are trying to find the fitting function y equal to f of x. So if you go back to the previous example, f of x is nothing but v equal to IR. Okay. Now for each x value you have two y values. One, the experimental value y1, which you obtained by performing an experiment. Two is the theoretical value which you get from the fitting function. For example, when x equal to x1, the experimental value is y1, the theoretical value is going to be f of x1. Now, if your fit is perfect, then the experimental value will be exactly same as the theoretical value. Most of the cases that doesn't happen. There is a slight difference between these two, and the difference is known as residual or error. So at point x1, y1, the residual is defined as E1 equal to y1 minus f of x1, the difference between experimental value and the theoretical value. So you calculate the errors or residual at each of the points. So you have n residuals here, and the total error is going to be sum of all these individual errors or all these individual residuals. But if you look at this graph, for example, if you focus at this point, here the experimental value is higher than the theoretical value, right? So if you calculate the residual here, it's going to be a positive residual. On the other hand, if you look at this blue dot here, the experimental value is less than the theoretical value. So at this point, residual is going to be negative. So the sign of the residual could be different at each of these points. So in order to get rid of the sign, what we do, we take the square of the residuals. Okay, so now I have only positive residuals. So the total error is defined as sum of the squares of the individual residuals. So the total error, I denote it by capital letter E. E is defined as E1 square plus E2 square plus all the way to En square, which is nothing but y1 minus f of x1 square, this is the residual at the first point, plus y2 minus f of x2 square, this is the second point residual, all the way to yn minus f of xn square. Now, as I said, E is a measure of the total error, or E is a measure of how well the curve y equal to f of x fits the given data set. So for the best fit, expectedly E should be minimum, the error should be minimum, or the difference between the experimental data and the theoretical fit should be minimum. This is known as principle of least squares. So some of the common fits which we use in physics are straight line fit, which is what we have discussed in the case of an ohmic resistor. This is a straight line fit. Similarly, you have parabolic fit. For example, if you take a simple pendulum and if you plot its potential energy or kinetic energy as a function of the displacement, and that's going to be a parabolic data, such data you cannot fit with a straight line, you have to go to a parabolic fit. Or if when you are studying an LR circuit or CR circuit, which you did in the last semester, you know that the behavior of current or charge is exponential. You have exponential growth of charges or exponential decay of current. In such cases, when you want to fit the experimental data, you need to go to an exponential fit. Now, for today's discussion, we will focus only on straight line fit. Now, before going into the details of straight line fit, I want to make one thing very clear here. Because in the first slide I said a best fit should pass through as many data points as possible. Okay. But that is not entirely true. For example, suppose you have this kind of an experimental data. Okay, so this is your x-axis, this is your y-axis. These are the data you obtained from your experiment. And you want to fit it with a straight line. So what should be the best fit? It should pass through maximum number of points possible. But you can see all the points are not in a straight line. For example, the first point and last point, they are in one line. So if you make a fit connecting first point and last point, then only 2 points are in the line. All others are out of line. So clearly that's not the best fit. So another option is drawing a line through these 3 data points. So at least 3 points match with the theoretical fit. So this could be one best fit according to our old definition, or alternatively you can have a fit like this. In this case also the theoretical curve passes through 3 experimental data points. But remember, we are following the principle of least squares. So we are not looking at whether our theoretical curve is passing through maximum number of data points. What we are doing is we find out the residual at each point, take the square of that and take the sum and see whether that total error or total residual is minimum. So for this particular case, when you find out capital E, you will find that in these 2 cases, even though the theoretical curve is passing through maximum number of data points, the residual or sum of squares of residual is not the minimum. So these 2 are not the best fit. So the actual best fit looks something like this. This is completely counterintuitive because here the theoretical curve doesn't pass through even one experimental data. But still, the residual or the sum of the squares of the residual is the minimum in this case. So remember, the best fit need not pass through maximum number of data points as long as the total error or the total residual is minimum. That gives you the best fit. So with this understanding, now we can move on to straight line fit. So once again, you have n data points x1, y1, x2, y2 all the way to x and yn. These data points you obtain by performing a physical experiment. Okay. Now you want to fit this data with a straight line. You know the general equation of a straight line, y equal to mx plus c. So your fitting function f of x is nothing but mx plus c. Now what do? You create this kind of a function. Now you have the experimental data. Now you also have the theoretical data, because you plug in the values of x, you can get the theoretical values of y. So there are two types of y values, experimental y, theoretical y. The difference between these two is the residual. So residual at the ith point ei equal to yi minus mxi plus c, where I ranges from 1 to n. And capital E, which is the sum of squares of the residual, is nothing but sum over I from 1 to n, yi minus mxi plus c whole square. Now remember, for the best fit, E is minimum. So when a function is minimum, the derivative is going to be 0. So if you take this particular form of the function, the derivative of E with respect to m should be 0. Similarly, derivative of E with respect to c should be 0. So let's first calculate dou E by dou c. So let's first take the derivative of the first term, that is y1 minus mx1 plus c whole square. Apply the chain rule. This is going to be 2 y1 minus mx1 plus c, then derivative of the term inside the bracket with respect to c. Derivative of y1 with respect to c is going to be 0. Derivative of mx1 with respect to c is going to be 0. And derivative of c with respect to c is 1. There is a minus sign here. So you have minus 2 into y1 minus mx1 plus c. Similarly, for the second term, y2 minus mx2 plus c whole square, the derivative is going to be minus 2 y2 minus mx2 plus c all the way to minus 2 yn minus mxn plus c equal to 0. Minus 2 is common, take it to the right hand side, it gets cancelled. Now you can expand the terms inside the bracket. So the first term is going to be y1 minus mx1 minus c, plus second term is y2 minus mx2 minus c all the way to yn minus mxn minus c equal to 0. So let's keep all the y terms on one side and take all other terms on the other side. So what are the y terms? y1 plus y2 all the way to yn. This is nothing but summation over I yi. And what are the terms on the other side? You have mx1 plus mx2 plus mx3 all the way to mxn. This is nothing but m into summation over xi. Plus, then you have c here, c here, c here. You have n c's here, which is nothing but plus n into c. So m summation over xi plus nc equal to summation yi. This is your first equation. Same way, now you can calculate dou E by dou M. Once again, apply the chain rule. So you have 2 into y1 minus mx1 plus c. Then you have to find the derivative with respect to m of the term inside the bracket. So derivative of y1 with respect to m is going to be 0. Derivative of minus mx1 with respect to m is going to be minus x1. Derivative of c with respect to m is going to be 0. So the first term is going to be minus 2x1 into y1 minus mx1 plus c. Once you find out the first term, all other terms you can write directly. The second term is going to be minus 2x2 into y2 minus mx2 plus c all the way to minus 2xn into yn minus mxn plus c. This is equal to 0. Once again, minus 2 is common. Take it to the right hand side. It cancels. So also you expand the terms inside the brackets. So you have x1 into y1 minus mx1 minus c plus x2 into y2 minus mx2 minus c all the way to xn into yn minus mxn minus c equal to 0. So xy terms you keep on one side and all other terms you take to the other side. So you have x1 y1 plus x2 y2 all the way to xn yn. This is nothing but summation over I xi yi. This is equal to, on the right hand side or on the other side you have m into x1 square plus m into x2 square all the way to m into xn square. This is m into summation over I xi square plus c into x1 plus c into x2 all the way to c into xn. This is c into summation over I xi. So you have the second equation, m summation over I xi square plus c into summation over I xi equal to summation over I xi yi. So you have two unknowns m and c. You also have two equations 1 and 2. Two equations, two unknown. You know how to solve this. When you do that, you get the unknown constants m equal to n into summation over I xi yi minus summation over I xi into summation over I yi divided by n into summation over I xi square minus summation over xi whole square. Similarly, c is equal to summation over I yi into summation over I xi square minus summation over I xi into summation over I xi yi divided by the same denominator. Denominator is common for both m and c. Once you find the values of m and c, now you can write down the equation of the best fit y equal to mx plus c. Even though the equation looks very cumbersome, the problem solving method is very simple. Okay, so let's get a hang of it using a practical example. Calculate the best linear fit for the following experimental data set. Okay, so you have performed some experiment. You have two variables x and y, and these are the values of x and y. You are asked to find a theoretical function, a theoretical straight line function which gives the best fit. Now what should we do? Basically we need to find the function y equal to mx plus c, where x and y values are already given. You need to find out the values of m and c. So these are the equations of m and c. So what all you need? You need the number of data points which you have from your problem, from your question. Then you need to find sum of x values, sum of y values, sum of x square values, and sum of xy values. So basically you need to create a table having 4 columns. 1 x values, 2 y values, 3 x square values, 4 xy values. Okay, so this is the first step. Okay, so x and y values are given. Now what are the x square values? When x equal to 2, x square equal to 4. When x equal to 4, x square equal to 16. Similarly, you find all the x square values. Now you find the x into y values. X equal to 2, y equal to 3, xy equal to 6. X equal to 4, y equal to 6.12, xy equal to 24.48. So carefully calculate all the xy values. Okay. So once you have all these 4 columns, now you calculate the sum values. Okay. So summation over IXI, this is nothing but 2 plus 4 plus 6 plus 8 plus 10 plus 12 plus 14, which is 56. Same way, you carefully calculate the summation over y values, which is 84.35, summation over x square, which is 560. Similarly, sum of xy, which is 842.4. So, and what is n? Number of data points 1, 2, 3, 4, 5, 6, 7. So n equal to 7. So you have all the parameters required for the calculation of the best fit available here. Now what you do? You directly substitute them in the equation. So let's first calculate m. So this is the equation for m. So n equal to 7. Summation over I, xi, yi is 842.4 minus sum of x is 56 into sum of y is 84.35 divided by n7 into sum of x square is 560 minus sum of x 56 square. This is equal to 1.496. Same way calculate c, this is 0.078. So once you find the values of m and c, now you can write down the equation of the best fit y equal to mx plus c, which is 1.49x plus 0.078. So once you get the fitting function, now for any x value you can calculate the corresponding y value. For example, what is the value of y when x equal to 100? So this is not there in the experimental data set, but since you have the theoretical function ready, you can make the prediction. Simply you put x equal to 100 in this equation, you get the corresponding y value. So if you want to see graphically how does this this data look like, so this is how it looks like. Here the black dots are the experimental data, which is nothing but your x and y columns, and the red line is the theoretical fit obtained using this particular function. So you can see that it matches with the experimental data in almost all locations. The next question, how do you do this straight line fitting using Python programming platform? So once again, remember what are the information we require. We need the x and y values, that's our input. Then you need to calculate sum of x, sum of y, sum of x square, sum of xy. Once you have these, and also the number of data points, once you have this information, you straight away substitute it in the equation. Okay. So let's first initialize the sum values. Sum x equal to 0, sum y equal to 0, sum xx, this is sum of x square, that is initialized to 0, sum xy, that is also initialized to 0. So we have 4 variables already initialized. Then you need to input the number of data points. So n equal to int input, enter the number of data pairs. Now I am going to input the data points one by one. Since I have n data points, I need to invoke a loop of n iterations. So I can do that using the range function for I in range n. So this will create a sequence of n elements. If you want, you can input x and y separately, but a smarter approach is to input them together using the split function. So you know the syntax for split function, x comma y equal to index for x in input, enter the x and y values dot split bracket. So here x is a dummy variable, you can put any name here, doesn't matter. So, and if you don't put anything inside the bracket, you will have to feed the data points separated by a space. Okay. So in each iteration, you input the x and y. Once you do that, simultaneously you can calculate the sum of the elements in that sequence. So sum x equal to sum x plus x. So let's see in the previous example what's going to happen. Sum x original value equal to 0. In the first iteration, the value of x equal to 2. So sum x is going to be 0 plus 2, which is 2. In the second iteration, the second value of x is 4. So sum x is 2. So sum x is going to be 2 plus the new value of x, which is 4. 2 plus 4 equal to 6. So in each iteration, the sum x gets modified. At the end of the nth iteration, you have the total sum of all the x values here. Same way, sum y equal to sum y plus y, sum xx equal to sum xx plus x into x. This will give you the sum of all the x squared terms. Similarly, sum xy equal to sum xy plus x into y. So basically, all the parameters are ready. Now directly you substitute in the equation. So m equal to, if you want, you can look at the original equation. So m is going to be n into sum xy minus sum x into sum y divided by n into sum xx minus sum x whole square, or sum x into sum x. Same way, you write down the corresponding equation for C also. So once m and c are determined, you can directly print the result. Print the equation of the best fit is y equal to m is the variable, so you don't put the quotation mark here, m comma x plus comma c. That's the m. Very simple, right? So even though the derivation and the equations are pretty bulky, the problem solving and also the programming are very, very simple. So this is one of the methods in which you can do the program. As always, you can find any number of ways to do this program. It's up to your logic, your programming sense. So I can give you a homework. You can do it using an alternative approach. If you look at this program, the majority of the program is dedicated to inputting the data and also finding the sum of x, y, x square and xy terms, right? You can simplify this. How? Suppose you are doing a program for the previous problem. So in that problem, x and y values are already given. Okay. So you can input all the x and y values directly. You can define it as a list. Okay, so x equal to 2, 4, 6, 8, 10, 12, 14. So directly you define the list. Similarly, y list also you define. In that way, you can skip the inputting part. Okay. Second, how you find out the number of data points? This is a list. You simply use the len function. So n is also up here. Now you need to find sum of x, y, x square and xy. So to find sum of x square and xy, first you need to create the list x square and the list xy. So how do you multiply two lists using the numpy module? Okay. So in order to use numpy module, first you need to load numpy module. So you say from numpy import start. So this should come at the beginning of your program. Then you can use the multiply function. So x square, let me call it xx. This is equal to multiply x comma x. So it will create a list containing all the x squared terms. Similarly, xy, multiply x comma y. So this will create a list whose elements are nothing but product of x and y. So you have 4 lists now, x, y, x square, xy. Now how do you find the sum of elements of a list? Use the sum function, right? For example, sum x is going to be sum of x. So once you find these 4 lists and the corresponding sum, you can straight away go to the final substitution. So you say here m equal to n into sum xy, sum bracket xy minus sum bracket x into sum bracket y divided by the denominator. So you can do this as a homework and just compare these two programs and see which is easier for you. Okay. And if you want to find some other way in which you can make a smarter code, that is also welcome. So basically, more the number of programs you do, your programming logic and programming aptitude is going to improve. So that's for today. Thank you.